That's what I put on this slide. It's that what I thought that it would be good for treatment of thrombosis. For example, if you get a blood clot in a small capillary inside the brain, it's very difficult to attain, or you will need a good deal of medication. So maybe this kind of little guys will we can deliver directly the drugs inside the capillary. And their targeted delivery, I think it's self-explanatory. Maybe we can include some lab-on-chip analysis systems on the labs. I told you that we are trying to put PN diodes, and maybe someday neural probing, including fat proteins that Professor Lee will talk about later, I guess. Thank you for your attention.
Simone, a fantastic and really mind-blowing presentation. Congratulations on all of your good work. I know that there are several questions and people have good ideas as well to suggest to you. So first question. Yes, please.
I'm Tad Hogue. A very interesting presentation. I wonder if you've looked at all at some of the hydrodynamic effects of having several of these swimming close to each other, because that low Reynolds number, there can be a lot of
not yet, but we are looking into, like I showed you, we have started to doing some basic finite element simulations of this hydrodynamics around these guys. It looks like from the first results that the flow stays very laminar around. So I don't think that, even if they are really close, I don't think they will have a negative effect on each other. Actually, there is a negative effect for our experiments inside the microchannel. If you create an electroosmosis effect in the microchannel, you also create a flow of the liquid, not only the motion of the robot. So you have to counteract the flow in the microchannel to isolate only the motion of the robot. That's the major difficulty now that we are facing for the experiments.
Dr. Borges, you were a pioneer of cardiological radiology, so I'm sure you must have quite a few applications in mind here.
I do, but for marketing purposes, you might call them nanoflagella. They look, as a zoologist, they look more like flagella than belts to me.
Yeah, well, that's the name of the guys, nanobelts. Actually, the name that we have chosen for the robots are nomads.
Nomads, I like
nomads,
that.
as in nanomedical robots for diagnosis and analysis.
I love it. I love it. Just a comment.
Thank you.
Yes, both one and then two.
Yeah, I like very much your approach because I think you go from the needs. You look for what has to be done and then try to fit your system to this and not doing the other way around, which many people are saying, we have this system, let's see what we can do with it, and then they kind of rape the things to work. So I think that's, and you're also using a lot of unknown information, although you don't refer to it directly. What's known in the coloring chemistry, you know, when you put things in electric fields, there are 4 different things that can happen. Electroosmosis, electrokinetics, electrophoresis, all this stuff, and you put them there in a very straightforward way. So I think you can learn a lot from going back to the old books. Even hard to find anymore on the information data, and really apply them here. But I think the fact that you're really using small particles and take advantage of well-known properties will bring you far along the way. I think it's very nice.
Thank you very much.
Hi, Jay Hickman, UCF. Very interesting work, very nice.
Thank you.
Question though, you had it at the last slide on the bottom, which was the surface chemistry.
Yeah.
And that could be really important or really detrimental to what you're trying to do. Have you put this into a protein-rich solution at this point?
No, not yet.
Okay, because, yeah, and also as you vary the osmolarity, to that changes their capabilities as well?
Exactly.
Yeah.
Exactly. That's one of the points that I haven't mentioned. For example, I talk about DNA. DNA hybridization, especially that what we are planning to use for the assembly, is very sensitive to the ionic concentration of the medium. So we don't still really know what will happen. Actually, we have produced some molecular level simulation of the DNA hybridization, and we want to try to include them the electric field inside to see that how effect is going to be on the biochemical reactions. But you got very, I mean, we've got very, very little experience on this kind of stuff, so we are looking for collaborations on this, actually.
Well,
So if you're interested.
I'm a surface chemist, so this is why I'm asking. So just one little follow-up, though, because it might be really interesting if you can selectively derivatize them, you know, for sensing with antibodies or something. You can actually look at the detection of the change in motion.
Yeah.
But also the problem you're going to have is non-specific absorption.
Yes.
Because you're going to really dampen out your effect if you start getting too much non-specific absorption, especially if you're in things like blood.
Yeah.
Cerebral spinal fluid might be a lot better because you're looking at 8% protein versus 0.001.
Yeah.
So there might be some trade-offs there that are interesting in terms of sensing where if you actually encounter, you know, an antibody or something else like that, if you have an antibody on your system, okay, you could actually look at a change in motion to say we've detected release of X.
Yeah.
Okay, if you can overcome that non-specific absorption component. And the problem is just making it hydrophobic, even with polyethylene glycols, you still get about 1, 2, 3% protein absorption. And I'm not sure in a system like that whether or not that's going to be significant or not. So you should take a look at that.
Okay, thank you. Yeah, the hydrophobic side, there's actually, what we are looking for hydrophobicity, it's to increase the locomotion, actually. We haven't thought at all from a biochemical interaction side. But very, very, very good remark. Thank you very much.
Well, what's going to be really necessary, if you're going to make them useful, is you're going to have to coat them with something that's going to stop
definitely.
absorption. Hydrophobic is a good first step to polyethylene glycols, but they're not, you know, we've measured down to, we still get 2, 3, 4% protein absorption, well, even on a polyethylene glycol layer. And I'm not sure how much that's going to interfere with your motion.
Okay. Okay, thank you.
Can you comment on the toxicity of the materials of which these are made and the degree
Well,
to which
actually,
that can be solved?
Yeah, I was expecting the question. It came late. Actually, there is very little works on the toxicity of indium gallium arsenide. It is considered that it is, actually. But, well, like Professor Bush has said, there's lots of toxic material that you put inside the body already. And that we hope that with proper surface chemistry that we would overcome this. But definitely there is specific actions to be taken towards the toxicity of these guys.
Well, maybe you could make it work by only putting one of these in the body.
Maybe. It would be very good.